Okay, good morning, everybody. I hope all is well. Um, I want to say to you guys, if you go to our browser, and there we are. Okay, go to our browser. Well, it's nothing really in the browser, but let's go take a look. 262. We were working with it's the online transition. We were working with the calculus of polar curves, and these are sort of the worksheet here I granted you guys here on some of the notes, some of the ideas. So what I'm going to do now today here is, I'm going to get to you guys, like I said, more examples of what to do with calculus of polar curves, and I'm going to upload that to you guys this weekend here. So yes, you'll get additional examples, and again, we'll put them over in the example portion that we've been doing, and you guys could click on those examples and see some more nice work there. But what I'm going to do now, today here, is we're going to talk about chapter 12, which is a very important chapter. It's on sequence and series. And I want to get started and at least see what we can do with some of these, because this is going to be what we do really for the rest of the semester, or the rest of the term here. So, let's see what we can do. I want to make sure we can get some of this in. I first want to start with the definition here of what we call a sequence. So, a sequence is really just what we say a list of numbers in a definite order. So, we can say it's a list of numbers in a definite order. And as you guys know, we actually, because we're talking about a list, there's something that kind of is some great detail. A list, formally in mathematics, is a set. So you'll see notation wise things like this, and I'm going to put it this way: 1, 2, 3, 4, 5. This goes on forever. Well, there's a list of numbers, and it comes in an order, meaning as you read left to right, the first, what we call term, is 1, the second term is 2, and so on. So here's a list. It's a sequence. And we could write another sequence. We can start with 1, and we could put 1/2, 1/3, 1/4, put the 3 dots, and this sequence, again, continues on forever like the prior one. Here's another list of terms. And so you can see things like this. We call them sequences. We can even, for example, have 1/2, 1/4, 1/8, 1/16, and so on. We can even have negative values. You can say, what about -1, -3, -5? These are all what we call sequences. We can have alternate values. You say 1, -1/2, +1/3, -1/4, +1/5, forever. These are all sequences. And then we can have something like this: 2, 2, 2, 2, forever. Another sequence. And we can change that. We can say -2, +2, -2, +2, and so on. Anyway, I wanted to describe to you guys here, give you some examples of some sequences, but we also have to talk a little bit about notation here. Okay, so the notation that you see with a sequence very often will be, and I'll put this here. Here's the notation now. We have AN, where N starts maybe with 1, and it ends, and it really doesn't end. That means goes on forever, right? That means it goes on to infinity, I mean, it just continues forever, right?
To infinity and beyond.
This is what we're talking about. This just continues. And for this notation, what you really see is the terms, meaning you have A1, A2, A3 forever, notation wise. So this tells us where to start. We start with N being 1. That's a subscript down there, right? And so this is called really the first term of the sequence. And A2 is the second term of your sequence. A3 is the third term, and so on. And again, this continues on forever by putting the dots. I can stop this somewhere. I can say, hey, instead of infinity, put K, and in that case, we'll have a kth term, and it will end, at that particular term. But, we really don't concern ourselves with that, but let's write this down. Let's note. They can say, how about if they give you AN, where N starts with 1 and it ends with K. Here's what that looks like, A1, A2, and all the way up to AK. So there you go. This is kind of where we can have a finite number of terms and an infinite number of terms. We have a finite sequence and we have an infinite sequence. Okay, so this is notation. And in speaking of notation, sometimes you just see something like this, AN, without the starting and ending point. That's assumed to be, if you see this blank, that's assumed to be where you start with the index of 1 and you end at infinity. That's the assumption. So if it's blank, you see it that way too. We also see, in terms of notation, which is going to be important, we also see the notation in terms of a function, functional notation, where AN is Fn, and of course, we say N is a natural number, and you say, what's the natural number? 1, 2, 3, and so on. So this is another way we can describe these sequences, and we're looking at some notation. And this is functional notation, and I'm going to say here, your domain, since N is a natural number, and that's what we're saying, right? The domain is a set of natural numbers. So your input values here are these kind of numbers. Okay? So that's the domain of this function. And we're going to start to really use this in great detail. So I'm going to put here a star around this one, but we're introducing some notation here for you. And then if I go back to this original definition, I could describe this for you guys and say, hey, this is what we can do. This here is simply the sequence N, where N starts with 1 and it goes to 100. It's the natural numbers. So we can show you really what this looks like. Here, this is 1 over N, 1 to infinity. Here, this is 1 over 2 to the nth power. And we're running out of space. So these are some things I generated this morning here for you to give you some definitions here. And this here is interesting. That's odd numbers. So we're going to put negative 2n plus 1. And we can say here, really, we can start at 0 even. Or I can adjust this. I can start at 1. Let's adjust it. So we start at 1, really. So this morning, let's kind of make that. We're going to put a minus 1. And that goes on forever. This is what this equals. And then we have an interesting sequence here. The difference between the one I just wrote down is that this is an alternating sequence. And alternating sequences are really sequences that alternate between a positive and a negative. So I'm going to say to you, we have an alternating way to describe things. And that's going to raise this to that we can say n plus 1 power. And notice that if I use n is 1, 2, 3, and so on, it's negative 1 to the first, negative 1 to the second, negative 1 to the third. That's going to change your sign. And when they mean alternating sequence, it's just referring to the sign of the terms. It alternates forever, positive and negative. And then you say, well, what's the denominator doing? Well, that's just increasing by n, by 1. So here's a very famous, what we call alternating sequence. And we see those. We're going to work with those. This is another example here of what we call a constant sequence. So we say, why is that a constant sequence? Because it's constantly a single value. And so we can describe notation-wise n is 1 to infinity, the constant sequence. And then you can say, well, the next one is a combination of the last two examples. This is an alternating sequence because it alternates signs, but you don't have to start with a positive like we did up here. This one started with a negative. And so we can fix that, or we can describe that notation-wise. I can say negative 1 to the n, and this is times 2, where n starts at 1 to infinity. And if I plug in 1, negative 1 to the first power is negative 1, and then negative 1 times 2 is, in fact, that negative 2. And then n is 2. Well, we square the power there for negative 1. That's positive. And then 1 times 2 is 2. So this will alternate in sign. That's why we call it an alternating sequence. Alternates in sign, really. Plus or minus. Okay. There's another example. But I want to emphasize we have various ways to write this alternating component for your sequences. And that's an alternating component. So here's just some examples of sequences and their notation. And we can actually talk about some recursive forms. And we can describe sequences that way. We have a very, very famous recursive sequence called the Fibonacci sequence. And that's when we have a formula here. And they have Fn. They have a way to describe this. Fn is Fn minus 1 plus Fn minus 2. Now remember, n is a natural number, or n comes from the set 1, 2, 3, and that goes on forever. So if you said, well, how do I generate terms of this particular sequence when it's given to me recursively? Here's what you're supposed to do. You're supposed to plug in. You're going to need the first term, right? You say, okay, I'm going to plug in 1 for n, and you get that f of 1 is f of 1 minus 1 plus f of 1 minus 2. And then you say, well, Mr. Judge, that's kind of bizarre because you got f of 0, and you got f of negative 1, what just happened? Well, there's more here. They give you the first two terms of the sequence. So for the Fibonacci sequence, the additional information they give us is that f of 1 is the same as the value f of 2. They're both 1. So this sequence doesn't start when n is 1. It does. Let's go back. They gave us, let's don't want to do that. I want to do this. They gave us the first term and the second term. So this is my first term of the sequence. Here's the second term of the sequence. And what you're going to do now to get the third term, they're going to tell you n starts with 3. So this is how we can start to generate the terms of our sequence. So we can say, okay, if n starts with 3 now, instead of plugging 1 in, you plug in the 3. So I have 3 here, 3 here, 3 here, and we get f of 3 becomes, well, 3 minus 1 is 2, and then 3 minus 2 is 1. So the third term really is the sum of the prior two, and that's a Fibonacci sequence. That third term is the sum of the prior two. It is the sum of f2 plus f1. And if we said, okay, this is interesting information, we want to find f4. Now, f4 happens when we plug in 4. So we plug in 4 for n. 4, 4. Notice what this gives us. 4 minus 1 is 3. 4 minus 2 is 2. We did the arithmetic right up here, right? N minus 1, plug in 4. N minus 2, plug in 4. Notice you get the fourth term is a sum, again, of the prior two. And that's Fibonacci. So the prior two, we say F3 we found was, this was 2, and F2 they gave us as 1. So this sum is actually 3. So this is how we start to generate terms. Now, I could remark and say to you, and I'm going to find some space, the Fibonacci sequence, 1, 1, we can think always as add the prior two terms to get the next term. So we're going to say 1 plus 1, we know is 2. That's the third term. 2 plus 1, the prior two terms, is 3. Okay. The fifth term, add the prior 2, because that's what this is. Okay, so if we really look at the detail and we get rid of this color, these are the prior 2 terms. Okay, so you have Fn, n minus 1. Well, that's how old you were last year, right? N minus 2, that's how old you were 2 years ago. So just keep adding the prior terms. This will be 5, and then 8, and then we have to add 5 and the 8, right? And that gives us 13. And then this is going to be 8 plus 13, that's 21. We do this pattern forever. And some sequences are defined this way recursively. So I want to introduce some of these things to you guys this morning, and then say to you, okay, here's the big deal. And you say, well, Mr. Judge, what's the big deal with these? Well, what's the big question? Here's what we want to know about sequences, okay? So I'm going to write this down. What we want to know about sequences, we want to know how our sequences end. that is an interesting kind of thing because we can model a lot of phenomena by using sequences. We want to know, how do they end? And what that really means is, how do sequences end? And I'll underline that, right? When we have a sequence, right, we have this thing called an, where n is 1 to infinity, meaning we have all these terms, goes on forever. How they end means, really, what's the behavior as n gets big? And you say n's getting big, yeah, as n goes to what?
To infinity and beyond.
Yes. How do they end? It's like end behavior. So the irony is, in some ways, you know a lot about this already, because we've already talked about these things as, again, n goes
to infinity and beyond.
We've seen it. End behavior. I'm going to say, here's what you guys have seen. I want you guys to know. You have seen the limit as x goes to infinity of f of x. This is, remember, in some ways, end behavior. You've seen more than that. You've seen x goes to really also minus infinity. But when it comes to our sequences, that's not what we're really talking about, because we want to look at natural numbers, 1, 2, 3, 4, all the way to, a never-ending idea, infinity, really. And so go back to the definition I mentioned, right? Recall what I said. I said, hey, we're going to look at these sequences as functions where the domain is natural numbers, right? Remember my domain? That D was natural numbers. So in essence, here's what we're really going to look at. Here's what we're going to consider. The limit as n goes to infinity of f of n. So that's where we're headed with all of this. That's going to be a big deal. So let's kind of think back to those days when we did the limit for functions. Let me draw something here for you guys. This is going to be a picture. It's going to be a challenge, but I'm thankfully, there you go. Thankfully, the iPad has a way to draw straight lines. And let me do something here. I'm going to do it this way. I know it's going to be skewed. And you say, okay, what does that mean? Well, take a look here. I know that's off axis there, right? Here's what I want you guys to focus on. Remember, when we looked at limits here, we really have two kinds of things. We have convergence and divergence. So this is what we care about when it comes to these limits. Do they converge, right? Or do they diverge? And we're going to give you these definitions. Where do they go? Do you go to some finite value L, and that's what's going to be what we have here? Or do they explode, right? Does it go to infinity? So here's the idea that we're looking for. Here's kind of how this might work. I can take your first example and say, here's my first term. We're here at 1. Here's my second term. This is the second term. Third term. Fourth term. And as you guys can see, yes, the terms are decreasing. I'm going to consider the following. I want the sequence to be 1 over n. Very simple example. If you recall from calculus or other math classes, this function is what you're looking at. It's a hyperbola. And it goes through these points. So if you guys remember here, this curve, 1 over x, well, all we're saying is, hey, change the variable. Don't use x, use n. So you're really looking at fn is 1 over n. Now, this is the graph. So if you recall from calculus 1, I could take the limit as x goes to infinity of that function, and I know that equals 0. It's a finite value. Well, what we're going to do now here is we're going to take the limit not for the x variable, but for the n variable, and that's 1 over n, and you're going to have the same exact answer. So limits at infinity are back. Okay, so we have limits at infinity, they're back. So if you've done this well the first time, good for you, you're going to do it well the second time. We're just going to change the variable from x to n. And so I'm going to have to give you some more definitions, and I'm going to get rid of, this here. I'm going to say, okay, let's actually do something like this. I guess we're way over here. How do I change the size? And we say, okay. Weird. I guess the second you erase anything, it's all gone. Yeah. Whatever. We can keep it. I think I wanted to just emphasize for you this thing here. It's my first point. Here's my first term of the sequence. Here's the second. Here's the third. Here's the fourth. And this goes forever. So we can say this point is 1, really A1, 1, A2. I'm sorry, that's a 2, A2, and so on. And then we get A3, A3, 4, A4, and forever. We know that those points are getting closer and closer to 0. They get so arbitrarily close. That's the idea behind a limit. So I got to give you a definition here of what's going to be important for us. Here's what we want to know. Let's write it down. I'm going to write it in black here. Definitions. Definition. When a sequence an has a limit L. Here's what this means. We can write it different ways. This is the limit as n goes to infinity of an equals L. Another way I like to write this, or will maybe like to see this, is we can say an goes to L as n goes to infinity. Sometimes people say as n gets big, the sequence goes to some finite value L. This has to be finite, a number. Finite number. So the sequence goes to some number. This is what we call, when this happens, we say the sequence converges. And that's what I mean. We have a convergent sequence. And I'm going to give you a note. Here's a big note, and maybe we should write it this way. Note. Otherwise, the sequence, otherwise, meaning when this doesn't happen, otherwise the sequence is known to diverge. So I'm going to give you guys my notes here. And how you can look at that is another idea, just to give you a fact about this, to really consolidate this. If the limit as x goes to infinity, f of x is L, and an is fn for, your domain being natural numbers, then we can say that that limit n goes to infinity of fn is also L. And that's just what we actually described when I went through this demonstration here for you. Just a very simple demonstration. I have to give you guys a formal picture. This is important here, right? Here's our formal definition, and it's deep. This is what you guys want to, consider. Right? The formal definition of convergence. Here's how they set this up. We say a sequence. It's weird. This iPad automatically, for some reason, goes to the erase, you know, all the time. That really throws me off. Here's your formal definition. You have a sequence. AN has a limit L. We write it the way I told you, right? You say, oh, limit AN equals L as n goes to infinity. Yes. But here's the formal part. Here's what this really means. It means the following. For every epsilon greater than 0, for every epsilon greater than 0, that means for every positive number, there is another number. There is a natural number n. There's a natural number n such that the absolute value of an minus L is less than that epsilon value whenever n is bigger than that natural number. Okay. This, ladies and gentlemen, is a very deep and powerful definition. You may take some time here to try to learn and study this definition. You may take a lot of time to think about this. It's very powerful. And I'm going to go into some of the details for you guys so that you guys know, right? Because it's actually really a picture of what you guys are looking at over here. It's really this. And here's what I'm saying to you. Start with this. For every positive number epsilon greater than 0, means every, for every positive number, typically what we're going to see is this epsilon is going to be a small value. So you're going to make epsilon small. Well, what they're saying is there's a natural number n such that we have this equation here. All right, so I'm going to go back here. No, we don't want to erase. See, it always goes to erase automatically. Weird. There is a natural number n such that we have this absolute value inequality. Now, I want to take a little bit of time to talk about that inequality. Let's actually see what this means. So I'm going to say to you guys, what does that mean? We have the absolute value, an minus L, less than epsilon. By definition, this is equivalent to minus epsilon is less than an minus L, which is less than epsilon. I can solve for an. I can solve for an. I'm going to add L to the middle, the right, and the left. And you say, well, what does that give you? Well, that gives me L minus epsilon now is less than an, which is less than L plus epsilon. This here, that's weird. This here is the inequality you want to think about. Okay? So that statement is exactly the same as this statement. So here's what's going on. They're saying that there is a natural number. So if you give me an epsilon, we're going to have a natural number where this inequality holds whenever we have this n here greater than big N. Now, let me explain these details. If we go back to the example, or I should say, let me create another example of that. Let me draw another picture for you. We'll do it in general and then see it in particular. And let's do it this way. And you say, why are you skewing my x and y axes? Well, because we don't care about negative values. We only care about the positive values. And then I'm going to change this here. I'm going to say, okay, we're going to have this line here. Let's change the color. Let's change it to, I guess we'll try purple today. This is the line, really, y is L, or I should say that's L. And is that straight? No, it's not straight. I'm going to draw a straight line if I can. Hopefully that's straight. So here's that line L. And it's really y equals L since it's a horizontal line, right, from algebra. Here's where your epsilon comes in. Let's change our colors. You give me some positive epsilon, any positive number. This is L. And if I focus on here, L minus epsilon, well, that's a little bit less. So how that would look, I can say, is something like this. This would be L minus epsilon. And the other value up here, L plus epsilon, let's write it this way. Here's L plus epsilon. Okay, now what's in the middle here? They're saying here, for every positive number, there exists a natural number n. They exist right here. There is a natural number n, whatever number that is, who cares? It's a natural number, such that this inequality is true whenever this little n, this represents the terms of your sequence. So how your sequence starts doesn't really matter. We can say our first term is here. Sorry. Our first term is here. It's second term and so on. Doesn't matter, right? This is how my thing behaves. But eventually, for some n, whether I like it or not, every term is in this tunnel. This is called an epsilon tunnel. This is an epsilon neighborhood. Epsilon tunnel. This is where we say, you give me any epsilon, eventually the terms of our sequence will be living in an epsilon tunnel centered around that value L. That's what we mean by convergence. Remember, this is the first term. This is the second term. This is the third term, the fourth, the fifth, the sixth. So starting on the seventh term and forevermore, we're in the epsilon tunnel. This is what they mean by this language, right? Eventually, the terms starting, and you say, what, that has to be bigger in this case, 6, that's the natural number. Eventually, every term is going to be in the tunnel. Every term of the sequence starting after 6 is in this tunnel, because then we have the 8th, 9th, 10th, and so on. So as n gets to infinity, we just get closer and closer to that value L. Now, this happens for every epsilon. So if I change that number, I can make epsilon super small. Epsilon could be 1/10. Eventually, there's a natural number n where every term will be in that tunnel, the epsilon neighborhood, around L. Oh, you want a smaller value of epsilon, 1/100th. Okay. It might be that, n would be a million. And after that a millionth term, every term will be in the epsilon neighborhood, the epsilon tunnel. So you could make this epsilon so small, it's arbitrarily small, 1/1 gazillion, right? Eventually, the terms of the sequence will be in this tunnel, epsilon neighborhood. This is the idea behind convergence. This is the formal definition, and this is deep. This might take people the rest of the semester to understand the definition. And some of you guys may not even understand the definition till the next course you take, or even the next, there's a course called Advanced Calculus. And that's when you really study the formal definition. So there's a lot of formality here, and this is beautiful, ladies and gentlemen. This is where the math really is. Every term, remember, this is the terms of our, this is the terms. There is a natural number so that every value after that, every term, after that big N, you're in this neighborhood. And this is what we mean by convergence. And then you say, similarly, what do you mean by this other thing, divergence? What if this doesn't happen? Well, we have a way to describe divergence too. Here's the formal definition of divergence. So how did I write this here? I wrote it as formal. Yeah, it's under formal. This is, by the way, what we mean by convergence. So I'm going to write that somewhere here in our notes so we know that. This is convergence. Remember that? So for divergence, because we want to give you that too. I guess we're using, well, we started with black. Okay. We have, and they call that a definition. This is for divergence. We have that limit as n goes to infinity of an equals infinity. This is what this means. We're going to change that. For every positive number, they should really say integer. I'm sorry, they should say natural number. For every positive number m, there is an integer n, they should say natural number, such that the terms of the sequence, the terms an is bigger than m. And let's write this down. Whenever n is bigger than that natural number. Now remember, in red, I'm going to say this is the sequence. These are the terms, right? AN is a sequence. And what they're saying is that the terms are bigger than some m value. And the terms are bigger than m? Well, you give me any natural number. And it really should say, yeah, any natural number. A natural number is by default, right? Positive. So for any natural number called big M, the terms of my sequence right here, the terms will always be bigger than M for any natural number. So you say, give me a natural number of 1,000, a billion, a trillion. Well, guess what? The terms will always be what? Bigger than that number, always, because they said for every natural number, M, there is another integer such that, you know what? This just means this applies, this little subscript n down here, this applies to the terms of the sequence. So these two things are related, an and n. So this just means that all the terms will always be bigger than any natural number you think of. This is what we mean by the limit going to infinity. Now, a good example of this to show you how that works is if I said to you, let's consider, well, it looks like this. I mean, I can write it. You're considering the sequence that we just described earlier, just n. What's going on here is if we said, I'm going to take the limit now as n goes to infinity of n, this is going to be infinite. And you might say, well, how do I know that, Mr. Judge? Well, go back to calculus. What's the limit as x goes to infinity of x? Wasn't that infinity? Okay. So what they're going to say here, the terms of this sequence, you give me a number, a billion. Guess what? There's going to be terms that are bigger than that. That's what they're saying here. You give me a trillion. There's going to be terms that are always bigger than that number for some n, meaning eventually. Because you're really looking again, how do these things end? What's the end behavior? So this is an idea of divergence. And again, if you were to try to draw the picture of that, you go back to the line, equation of a line, that's all we did. And this maybe is more detail than you think you say you need. Again, goes back to eraser. But we're looking at, let's change the color. It has a slope of 1. So we're really looking at a line here. Let me double check. Sometimes I have to. There we go. N is 1. Here's my first term. 1. N is 2. Oh, 2. N is 3. 3. What they're really saying is these terms just go to infinity. And this is what we say, or what we call, divergence. And let's write that down. So the book gives you this as well. This is a divergence. Okay. All right. So now here's what I want to do once we give you guys the foundation of what we're doing. Let's look at some examples of these things. Well, before we do that, I guess we're going to talk. I'll give you quickly the limit laws. Now, these are limit laws that are analogous to the limit laws you guys already had for the real variables. Okay, so you had limit laws for real variables, and here's how we write them down. We're going to say the following. We're going to let an and bn be convergent sequences and C a constant. So all the limit laws you guys learned from Calculus 1, right? The limit of a sum is sum of limits. And remember, if they write it this way without talking about n going to infinity, ladies and gentlemen, it's by default. So they leave that out just to save some time and energy. So I just want to let you guys know. The limit of a difference is difference of limits. Okay. The limit of a constant times a sequence is the constant times the limit of the sequence. So this is just back from calculus. The limit of a constant sequence is a constant. Limit of a product is product of limits. And the limit of a quotient is quotient of limits. Okay, but you can't have actually, remember, bn can't be 0, and we can't have the limit of bn equal to 0. Okay, so we have those things because it has to be defined, right? So we usually have if, and then that brings us to 7. You say, well, what's 7? Well, here's what we're going to have. The limit of an to a power is equal to the limit of an to your power, and then we have to say something about the power, right? So remember the p here, we have to say if your power here is positive, so we need the positive power, and the terms are positive for an. Because again, if your terms are, if you're saying you're going to have a positive power, but your terms are negative, some of them, we're not talking calculus of complex numbers, right? So these terms here need to be positive. This is why they say that. And so now you can take like, and all that's required is p has to be positive. P could be a square root. So if you said, oh, okay, square root, of a negative is imaginary, well, that's the issue. And so let's look at some of these here. And I'm going to give you one last fact. Okay, so I'm going to give you a fact here that I'll prove for you. Not today, though, but I'll prove this one. If the limit of the absolute value equals 0, and yes, that's as n goes to infinity. So if you take the limit of the absolute value of the general term of a sequence, okay, essentially make every terms positive. That's all they're saying. Make the terms positive. Then what this means is the limit of an is also 0. So the idea here is you have convergence and you have convergence. Goes to 0 for both of these. So, I set the table for us to look at some examples here. And that's important. And so let's take a look at some examples and see whether they converge or diverge, right? So they're going to say to you, do the following limits converge or diverge? And first example, limit e to the n. So they're going to give us this limit here. A lot of times they just say, here's what they'll do. They'll say an is e to the n. All right. Then the limit of e to the n, as n gets big, you guys know, where does that go? This is the exponential function. This is going to be infinity. And you say, well, how do I know? Well, think about the limit as x goes to infinity, e to the x. This is the exponential growth curve. That goes to infinity. So that's using the idea I wrote about way back here. There we go. That's using what we talked about here. Right? This is exactly what we're talking about. So here's your first limit question. Another example. They say an is e to the minus n. Okay. Well, the limit then of e to the minus n as n gets big, remember, think of this in terms of x. That was 0. For the same reason, right? Because if this is e to the minus x, well, that's an exponential decay curve. And as x gets big, because that's the idea here, x gets big, or in this case, n gets big. How does this end, right? N goes to, again, infinity.
To infinity and beyond.
We're thinking end behavior. This is how the sequence ends. How about something like this? Let's talk about this here. You can say, what about if they give us a to the n equals e to the x, e to the n over n. And you say, okay, Mr. Judge, I'm going to do what you said to do. Take that limit of e to the n over n, and then we discover that the numerator grows without bound, and so does the denominator. They both grow without bound. Infinity over infinity. And then I'll say to you, okay, what does this mean? Well, what this means, ladies and gentlemen, is something very, very interesting. I say to you, this is something you know about. This is an indeterminate quotient. And so, technically, ladies and gentlemen, you may say, oh, Mr. Judge, do I apply L'Hopital's rule? And the answer is yes, you apply L'Hopital's rule. Absolutely, L'Hopital's rule. But you have a problem because L'Hopital's rule applies only to functions of real variables, meaning x has to be a real number, not a natural number. Well, that's not a big deal. Here's what we do. We go back and take the limit as x gets big of e to the x over x. We can apply L'Hopital's rule. And that gives us a limit as x goes to infinity of differentiate the numerator, which is e to the x, differentiate the denominator, which is 1. Remember, this is L'Hopital's rule. Yes, we're using L'Hopital's rule. So this limit is really going to be as x goes to infinity, e to the x, which equals infinity. So what this means here, since I went out to the real variable x, I can really now go back to the domain of natural numbers, and I can say, this is also infinity. That's what we say. But we also use the language now of diverges. So this sequence diverges, this sequence converges, and that's how we start to answer some of these particular questions. Okay. Let's use the fact I gave you guys. Let's see how this works here. This particular fact we talked about, the limit in absolute value. Now, here's what's going to happen. This applies only to, let's go back there. This really applies to only, I'm going to write it down, alternating sequences. So if you guys a big heads up that whenever they talk about the absolute value of the terms, it applies to really the alternating sequences or sequences that have negative values. It's another way of saying turn it positive. And you might go, okay, what's an example of that? Well, I'll give you a couple examples. They can say an is -1 over n. And in this case, you might say, well, then they want us to know, does that sequence converge or diverge? What we got to do is we got to take the absolute value of this. This is, I'll do every detail. The absolute value of an is the absolute value of -1 over n. Now, by properties of absolute values, you guys remember the absolute value of a quotient is quotient of absolute values. A little bit of algebra. And the absolute value of -1 is +1. The absolute value of n is n because n is a natural number. You say, what are those numbers? 1, 2, 3, and so on. This is what n is. So we get 1 over n, and that's going to be the absolute value of n. This is what they want us to use. Okay? So we just apply the absolute value of it because we have some negative terms there. And I apologize. There's another thing I didn't do. That's -n to the nth power. So there's a little bit more detail. Let me apologize there. I'm glad I caught it. I wanted to get this in here for you guys for this weekend because there's a little more. Everything's still the same. -1 to the n, absolute value of n. Now, my numerator, though, by definition is, this is going to be absolute value, -1 times -1 times -1. There's a lot more ideas here. We're focusing on that numerator. What does this mean? Okay, that's n is an exponent. So that means we have n of these. Okay, we're multiplying. All right, absolute value of -1, absolute value of -1, absolute value of -1. There's a product rule for absolute values, right? Because this is multiplication here. Times, 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 times. And again, times, 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 times. We have n of these. The same thing happens. Each one is 1. So I apologize. And then 1 times 1 times 1 times 1 is 1. And so, again, we end up with 1 over n. There we go. That's really what I wanted to demonstrate to you. The other one is a very trivial kind of example. This is something we see all the time in sequences, okay? We see this alternating mechanism. All the time. And so if we apply the theorem or the fact that I'm going to prove to you guys, not today, the limit as n goes to infinity, absolute value of an is really the limit of 1 over n. And we found out, or we know that this equals 0. That was our first example. So what this means is, if we go all the way back to the fact I gave you, okay? Important fact. And you have to know what an if-then statement is. It's a conditional. What that means is, if you have this limit equal to 0, and we do, good, we show that this limit in absolute value is 0. We know that. Here's what we can conclude. The limit of an is 0. We have convergence. So what that means about this original question is that the limit as n goes to infinity of negative, and that's going to be, let's put the alternating mechanism here, nth power, make sure that's in your notes. What we'll know is that this here is also 0. We also have convergence. That's what this statement says. So as you guys can see, there's a lot of work in this section. There's a lot of work in these first 2 sections, which is why I wanted to get started on them. I wanted to get at least this far so that I can give you guys some extra examples again of this over the weekend. So my chores are dedicated to Calculus 2 this weekend to get a couple of videos up on working more with finding the limits for sequences, essentially using calculus limits at infinity and using this theorem I gave you guys. So I'll get those examples up, examples of calculus of polar, some examples up there too, but I also have to grade your test. And so don't forget that your, the take-home portion of your test is due Monday before class. And yeah, I did send a communication about the typo for question 5. Question 5, the interval is 1 to 2. So I sent that in Canvas. I hope you guys got that. And yes, you just upload when you're done to, of course, the assignment portion called, whatever, completed test 3 take home. But for number 5, the interval is really from 1 to 2. And let me give you some homework in this book too, so you guys can get started and think about. Because there's a lot of work in this section. And 12.1 and 12.2 is a lot of work. Here we go. So you can say 12.1, you can start in 3 to 35. You can do them all. Okay, so anyway, got to get going. If you have any other questions, see me during office hours, and time for the next class. I went a little over. So try these out. Have a great weekend. And, again, I'll get those examples up. Take care.